Welcome to Gooseberry Science and Education videos. If you were to dive down into the Mariana Trench, the water pressure pressing against your body would be, well, it'd be roughly the equivalent of having 50 jumbo jets stacked onto your chest.
Yeah, just absolute instantaneous destruction.
Right, total crushing destruction for a human being. And yet, bizarrely, things actually live down there. I mean, they thrive in that environment.
It is completely counterintuitive to our terrestrial brains, honestly. We evolved to handle, roughly 14.7 pounds per square inch of atmospheric pressure.
Yeah, a cozy 14.7.
Exactly. So we look at the ocean, which covers a massive 70% of our planet, by the way. And because we literally cannot survive in it for more than a few minutes without specialized gear, it just registers as this alien dimension.
Totally.
It's right there, constantly shifting against our shores. But conceptually, it feels totally out of reach.
And that alien dimension is exactly what we're demystifying today. Our mission for this deep dive is to give you, the listener, the ultimate shortcut to understanding that hidden 70% of the Earth.
It's going to be a fun one.
Oh, absolutely.
Wow.
We're taking an exhilarating, full-speed-ahead tour of John Woodward's fascinating text, Voyage, Ocean. And we're not just doing some standard book review today right there. We are going to distill the absolute coolest, most mind-blowing facts and the underlying mechanics of our oceans into one cohesive journey.
Yeah, the goal here is that instead of feeling overwhelmed by the sheer scale of marine biology or oceanography, you walk away understanding exactly how this massive underwater machine actually works.
Precisely.
And the source material takes a really highly visual, immersive approach. It explicitly invites us to, quote, look through the porthole at this environment.
I love that framing.
Right. And when you do look through that metaphorical porthole, you don't just see a vast expanse of empty, uniform saltwater. You see a highly complex world. We're talking dramatic panoramas, deep plunging tectonic trenches, and stunning marine life that rivals and in many cases completely exceeds the biological diversity we have up here on land.
Okay, let's unpack this.
Yeah.
Because the history of how we view the ocean is just wild to me.
Oh, it really is.
The text emphasizes that for centuries, people merely sailed across the oceans to discover new lands. It was treated as just, a flat surface to get from point A to point B.
Just a two-dimensional highway.
Exactly. For thousands of years, humanity essentially stared at the closed cover of a book, completely ignoring the pages inside.
But I have to push back a little on the historical narrative here.
Okay, lay it on me.
Well, I refuse to believe it was just a matter of we didn't care. I mean, humans are relentlessly curious, right? We scaled freezing mountains and trekked across deadly deserts just because they were there.
That's true. So why did we stop at the shoreline? Was it really a lack of imagination, or was the ocean just an insurmountable physics problem until modern tech came along?
What's fascinating here is that you are entirely right to push back on that. It wasn't a lack of curiosity at all. It was a profound, lethal barrier of physics.
Because the density and the pressure.
Exactly. Water is roughly 800 times denser than air. It rapidly absorbs light, so it plunges you into absolute darkness within just a few hundred meters.
Wow, just a few hundred meters.
Yeah, and it absorbs body heat incredibly fast. And as you mentioned with the jumbo jets, the pressure increases by 1 atmosphere for every 10 meters you descend. So the ocean column actively fights human biology.
So it naturally bred a barrier of fear because venturing into it meant almost certain death.
Precisely. And the text highlights that it wasn't until relatively recent times, armed with amazing technology, specifically the pressure-resistant hulls of submersibles and the breathable air delivery systems of scuba gear, that explorers could finally overcome those physics.
They could actually investigate beneath the waves to physically map the ocean floor.
Exactly.
So technology was the crowbar that finally pried the cover of the book open. And the moment we slipped beneath the surface, that shift completely redefined our worldview, didn't it?
Oh, entirely. The ocean went from being perceived as that flat, horizontal highway for cargo ships to a highly complex, three-dimensional environment.
Because we discovered that the bottom of the ocean isn't just a flat, featureless, sandy basin.
Not at all. It is a dramatic panorama. I mean, we found towering underwater mountain ridges and massive plunging trenches that honestly make the Grand Canyon look like a pothole.
A pothole? That's insane to think about. And because technology finally allowed us to dive down and actually look at the topography, we realize the ocean isn't just one big, uniform bathtub.
Right.
It is divided into drastically different extreme neighborhoods. which completely changes how you have to think about marine geography.
It really does. And the text provides a brilliant global itinerary to showcase this. It maps out a journey through these distinct zones, and, well, the contrast is staggering when you understand the mechanics driving them.
Let's trace that itinerary, but I want to make sure we understand why these places look the way they do. So we start way up top, fully immersed in the freezing waters of the Arctic Ocean.
Brr.
Yeah, the source talks about the harsh winter ice, but also these crucial open areas of water surrounded by ice called polynyas, and obviously massive icebreakers literally smashing their way through the frozen seas. But what exactly is a polynya, and why does it actually matter?
So a polynya is essentially a naturally occurring persistent hole in the sea ice.
Like a lake in the middle of the ice.
Basically, yeah. And they are incredibly important. They are kept open either by howling offshore winds, literally pushing the ice away as it forms, or by upwelling currents of slightly warmer water from the deep ocean.
Oh, so the warm water stops it from freezing over.
Exactly. And because they stay open, they act as literal breathing holes for marine mammals like whales and seals during the brutal winter.
Wow.
Yeah, they are vital, isolated oases of life in an otherwise frozen desert.
That makes total sense. It's a localized physical phenomenon creating a biological hotspot. Now, if we move drastically in temperature and ecology, the journey continues down into the Atlantic Ocean.
Right, big shift.
Huge shift. The text points out an incredible contrast here. On one hand, you have the immense scale of the Amazon River. The source highlights how this massive river pours just, well, vast amounts of muddy water directly into the Atlantic. But this isn't just a color change, right?
Far from it. When the Amazon dumps that muddy terrestrial water into the Atlantic, it is injecting millions of gallons of fresh water into a saltwater environment.
Which don't mix well.
Right. Because fresh water is less dense than salt water, this massive muddy plume literally rides on top of the heavier ocean water. It alters the salinity and the physical buoyancy of the ocean for hundreds of miles off the coast.
Hundreds of miles. That's wild.
Yeah, and it blocks sunlight from reaching the depths below it, which completely shifts what kind of photosynthetic life can survive there. It's just a massive chemical and physical disruption.
And yet, in that exact same Atlantic Ocean, the text takes us to Ascension Island.
Oh, this is a great example.
Right. The source describes it as a dormant volcano erupting from near the mid-Atlantic ridge, marked by striking, stark black lava flows from past eruptions. I know the mid-Atlantic ridge is a massive underwater mountain range, but what is actually causing that?
So the mid-Atlantic ridge is the result of plate tectonics. You have the Earth's massive crustal plates actively pulling apart from each other deep underwater.
Like a seam splitting.
Exactly. And as they separate, magma from the Earth's mantle rises up to fill the gap, instantly cooling in the near-freezing deep ocean water to form new crusts.
And sometimes it piles up.
Yeah, occasionally it builds up high enough to break the surface, which is exactly how you get an isolated volcanic peak like Ascension Island.
So you have a massive influx of muddy, buoyant, fresh water, fundamentally altering the ocean's chemistry in one area, and jagged, fiery black lava rock violently tearing the ocean floor apart in another.
It's a lot of action.
It is. I look at this and wonder, how do we even classify these as connected bodies of water when the environments and physical rules seem so wildly different?
That is a brilliant question. The way to synthesize this is to understand that while local geography creates incredibly unique, isolated phenomena like the freshwater plume of the Amazon or a volcanic island, they are all just cogs in one massive interconnected planetary engine.
It sounds like you're describing a giant planetary circulatory system. Just like my heart pumps blood to regulate my body temperature, this ocean engine is pumping heat and matter all across the globe.
That is a perfect analogy. And the text provides a prime example of the pulse of the circulatory system by explaining the mechanics of the tides.
Oh, right.
Tides are a global phenomenon driven primarily by the gravitational pull of the moon and the sun.
All right, so the gravity of the moon essentially drags Earth's ocean water toward it, creating a physical bulge in the ocean.
Exactly. The water is actively responding to the gravitational force from space. But here is where the global engine meets local geography. That massive planetary gravitational wave is then forced to interact with the specific, jagged coastlines of the continents.
So it hits different shores differently.
Yeah, so the global pulse of the tide acts very differently depending on whether it's hitting the wide, muddy basin of the Amazon or slamming into the steep, rocky drop-offs of a volcanic island. The local topography amplifies or dampens the global force.
That is so cool. The water is all part of one connected circulatory system, but the local physical rules dictate how it behaves.
Exactly.
The text really drives this home when it talks about extreme phenomena. It mentions devastating tsunamis occurring in the Sunda Arc and intense cyclones whipping up in the Indian Ocean. I want to clarify the Sunda Arc for the listener because the source name drops it, but the mechanics are crucial.
Yes, so the Sunda Arc is a massive fault line near Indonesia. It is a subduction zone, meaning one tectonic plate is physically grinding underneath another, which builds up a ton of pressure, an unbelievable amount. And when the immense friction between those plates finally gives way, the seabed violently snaps upward. That sudden, massive displacement of water is what generates a tsunami.
So the local tectonic geography dictates the event, but the resulting kinetic energy is transferred through that same interconnected water we've been talking about.
You've got it.
And this massive engine of diverse habitats, temperatures, and pressures naturally leads to one thing: an absolute explosion of weird and wonderful life uniquely adapted to survive in these specific extreme neighborhoods.
Oh, the biological diversity, and more importantly, the sheer mechanical ingenuity of marine life is staggering.
Here's where it gets really interesting, because the biology revealed in the text is so highly specialized. Let's look at the very top layer of the ocean first.
Okay, the sunlit zone.
Right. The source highlights the community of plankton. It describes them as mostly small animals and microscopic plants that drift in the ocean, mainly near the sunlit surface. And the text notes that they are drawn to nutrients in areas where liquid water evaporates. But how exactly does evaporation equal food?
It comes down to the physics of phase changes. When surface water is heated by the sun and turns into vapor, only the pure H2O molecules escape into the atmosphere.
They leave the rest behind.
Exactly. The ocean doesn't evaporate its salts, its dissolved minerals, or its microscopic organic matter. All of those heavy, nutrient-rich compounds are left behind in the water.
So evaporation is basically boiling down a soup to make the broth more concentrated.
Precisely. It creates a highly concentrated, nutrient-dense layer at the surface. Plankton capitalize on this dynamic. These tiny, drifting organisms are the foundational base of the entire oceanic food web, turning sunlight and concentrated chemical nutrients into biological energy.
So you have these microscopic organisms soaking up a nutrient bath in the warm sun at the top of the water column. But then the deep dive takes us plunging down thousands of feet into the abyss, and we hit deep-sea bioluminescence.
Oh, my favorite part.
It's so cool. I always picture this like a bustling neon city thriving in pitch-black darkness with bizarre creatures generating their own light. But mechanistically speaking, how does a drifting community of plankton at the sunlit surface connect to the glowing predators of the deep? How does that ecosystem sustain itself without the sun?
If we connect this to the bigger picture, life in the ocean operates as an interconnected vertical column. Remember the circulatory system analogy?
Yeah.
Well, it works biologically, too. The energy generated by the plankton at the sunlit surface doesn't stay there. As those surface organisms die, they sink, creating a continuous shower of organic material known as marine snow.
Marine snow, wow.
Yeah, and that falling energy feeds the dark layers below.
But the creatures down there aren't just passively waiting for food to fall, right? They are actively hunting using bioluminescence.
Exactly. Down in the crushing dark, life uses chemistry to survive. Bioluminescence is typically a chemical reaction inside the creature's body involving a light-emitting molecule called luciferin.
Okay.
And the text makes it clear that they aren't just glowing for the fun of it. They use this light as a highly specialized tool. They use it to hunt, like the anglerfish dangling a glowing lure to attract prey in the dark. Or, surprisingly, they use it to hide.
Wait, how do you hide by glowing? Wouldn't that make you a massive target in the dark?
It sounds backwards, right? But it is a brilliant trick called counter-illumination.
Counter-illumination.
Yeah. If a predator is looking up from below, it might see the faint residual silhouette of a fish against the tiny amount of sunlight filtering down from the very surface. So some deep-sea fish have bioluminescent organs on their bellies that perfectly match the wavelength and intensity of that faint downwelling light.
No way.
Yes. It effectively erases their own shadow.
That is unbelievable. They are actively projecting an invisibility cloak by matching the background lighting.
It's pure genius.
It really underscores the takeaway from the text. From the bright sunlit zones to the deepest, darkest hydrothermal vents, marine life always finds a highly specialized physical or chemical way to exploit its environment. Every creature is a masterclass in adaptation.
Without question. They leverage whatever physical constraints they are handed to survive.
And speaking of a masterclass in physical adaptation, there is a specific image from the source that I absolutely love. It's the porcupine fish, also known as the puffer fish.
Oh, yeah, the classic puffer.
Yeah, the text shows it in its fully inflated state in a bright blue sunlit sea. Pop culture always portrays it as this comical, spiky beach ball that just magically blows up. But the actual mechanics of how it achieves that shape are wild.
It is a fascinating anatomical feat. When the porcupine fish senses a threat, it doesn't just hold its breath, it actively swallows massive amounts of water, or air, if it happens to be at the surface.
Okay.
It pumps that water into a highly elastic stomach that has evolved to expand to several times its normal size.
Right, and it's not just the stomach, is it? Its entire skeletal structure is designed for this. I read that their spine is highly flexible, and they lack a conventional rib cage, allowing their body to balloon outward without internal damage.
Yes. And as the skin stretches tight, the specialized spines that normally lay flat against its body are forced to stand straight up.
Ooh.
Exactly. It instantly transforms from a bite-sized fish into a rigid, spiky sphere that is physically impossible for most predators to fit into their mouths.
It is an incredible defense mechanism.
Yeah.
It perfectly encapsulates the bizarre mechanical biology of the ocean. But, as incredible and adaptable as this marine life is, the book makes a very clear shift.
A sobering one, yeah.
It highlights that the ocean's ecosystems are currently facing rapid, unprecedented changes. And these changes aren't coming from natural predators or shifting tectonic plates.
No, the current disruption is coming directly from above the surface.
From us. This marks a distinct transition in our deep dive into the ocean resources and troubled water sections of the source. We spent this time marveling at the majesty and the mechanics of the planetary engine, but the text outlines our massive human footprint on it.
And it's a heavy footprint.
It really is. We use the ocean heavily. We fish it on an industrial scale. We farm it. And we literally mine the seafloor for resources.
And the source material is very direct, presenting the facts about the severe modern consequences of this extraction and interaction. It explicitly features panels outlining the specific problems occurring in the waters today, focusing heavily on chemical pollution and the broader impacts of climate change.
And more importantly, the text outlines the physical consequences these disruptions will have for the future.
Right.
So, what does this all mean for you and me? I mean, you might be listening to this deep dive right now, sitting in traffic or in a high-rise office building or living in the American Midwest, completely landlocked. If you never actually see the ocean, is this Ultimate Explorer's Guide actually a warning manual in disguise?
This raises an important question about the fundamental purpose of understanding our planet. The value of mapping the ocean floor, of understanding the thermodynamics of the currents and the delicate chemistry of plankton, isn't just to satisfy our scientific curiosity. The text illustrates that the ocean isn't an isolated bubble.
Right, it's connected.
It is a highly reactive system.
Because if we dump heavy chemical pollution into the water or alter the global temperature, we aren't just harming some isolated fish. We are physically tampering with that massive planetary circulatory system we talked about earlier.
Exactly. And the thermodynamic and chemical consequences of tampering with that engine absolutely do not stay confined to the ocean. The ocean is the primary driver of the global climate. It absorbs massive amounts of solar heat and atmospheric carbon.
Right, which makes it highly personal for you, the listener.
Yeah.
It doesn't matter if you are standing on a rocky cliff staring at a coastal lighthouse,
Mm-hmm.
which, the book features prominently, or if you are living 1,000 miles inland, surrounded by cornfields, and have never tasted salt water.
It still affects you.
The physical health of the ocean directly impacts you. Its currents drive the weather patterns that bring rain to those inland farms. The massive resources we pull from it sustain global economies. If that interconnected planetary engine stutters, your daily life is impacted.
Yeah.
Your local weather changes. The ocean is not just a scenic place for marine life. It is the physical life support system for the entire planet.
The interconnectedness of these systems just cannot be overstated. From the evaporation at the surface to the deep ocean currents, terrestrial life is entirely dependent on that 70% of the map functioning correctly.
Which brings me back to a thought that has been lingering in my mind since we started this deep dive today. We've talked about how technology finally allowed us to dive down, to overcome the crushing pressure in the darkness. But the text explicitly states, and I quote, "Much of this watery world is still unknown."
It is a deeply humbling reality. For all our advanced submersibles and sonar mapping, it remains a frontier.
It really is. Think about our analogy from the very beginning. For thousands of years, humanity stared at the closed cover of a massive book. Then finally, we managed to pry it open.
We finally peeked inside.
Exactly. We understand how the Amazon alters salinity, we've seen the counter-illumination of deep-sea predators, and we understand the elastic stomach of the porcupine fish. But the absolute truth is we have only just begun to scratch the surface. We've barely skimmed the prologue.
That's a great way to put it.
So I want to leave you with a lingering thought to mull over today as you go about your routine. If we have only just begun to properly explore this crushing pitch-black space, what massive, reality-bending discoveries are still hiding in the dark? Are there strange, entirely new biochemical life forms waiting down there in the trenches, utilizing physics we haven't even documented yet?
It's very possible.
Are there vast, unknown underwater ecosystems that will force us to completely rewrite our understanding of how life functions on planet Earth? The next time you look at a globe, remember, that massive expanse of blue isn't just empty space. It is an active, churning, unsolved mystery just waiting for the next page to be turned.
Please like and subscribe if you enjoy the content.